I'll tell you what I've done. Since you wanted me to go through paper 5, right? This was actually what I gave to all my students. It's a crib sheet. It's have you heard of examiner's report before?
Or so, you know, is it the one that follows the mark scheme?
Marking scheme, yes, marking scheme is published as soon as results are released, and the exam report are usually released like around 2 months after results are released, and it's basically the people who mark the exam paper, and then they highlight important information that students always miss out on. So I don't have one for paper 4, but for paper 5, I always start off teaching my students with this particular thing. So that it's important to understand, right? Because paper 5 can be anything, because it's down to experimental science. It's the same deal with physics, with biology as well, but do you do biology or do you do physics? You do physics, right? Not biology, right?
Computer science.
Yeah. So yeah, I mean, what I'll do is I will, instead of going through everything, have you had a chance to do any paper 5 yet?
Oh, I was doing the most recent one, the 2021 May.
2021 June. May. Hang on. I'm just gonna copy. Do you know which paper code was that?
52.
52.
Oh, you took code 9701.
Yeah, 9701 is the subject code. Don't worry. I'll just copy onto my iPad so that we can discuss it in a little bit. But yeah, let me just go through some of the important content first. Has your teacher gone through any paper 5 with you yet? Or you're left on your own?
Not at all.
Not at all.
Not at all.
But you have the Cambridge textbook, right?
Yes.
Okay, so inside that textbook, there should be a chapter on experimental planning and design. Did you do actual practical or did you do alternative to practical for IGCSE?
Oh, IGCSE, we had the predicted grades.
Oh yeah, crap. Oh yeah. Because your batch didn't do the exam, right? But wait, when you were in school,
we didn't have actual practicals. No, we don't have any practicals.
Okay, so even when you were in school, you didn't do actual practical. You were just doing alternative to practical, was it?
Yes.
Okay, cool. That's actually my intention. In A level, there's no escaping paper 3 because there's no other alternative. Okay, you have to do paper 3. Paper 5, however, is to do with things that are less likely to be possible in paper 3. But then there are also cases. There are some very, very famous topic. Rate of reaction is number 1, very, very famous. They call it reaction kinetics. So basically, we talk about orders of reaction. We talk about graph. We talk about rate determining step. I think I have gone through rate of reaction with you, right? The A2 rate of reaction, haven't I?
Yeah.
Yep. So
I don't think we went through it.
Oh, we haven't gone through it. Okay, so in the A2 topic, if we have done.
But then it's not going to be in our exam because we haven't learned it in school yet.
Okay, cool. So that thing is actually a number 1 topic that usually comes up in paper 5. Number 2 most common topic is enthalpy change. So this is directly from your AS practical. So it's to do with that Q equal to MC delta T. And then you do delta H equal to Q divided by mole of the limiting reactant. This is number 1. Well, this is number 2 in the most popular thing that often come out. Okay. What else often come out? Yeah, I mean, these 2 are really, really common. The other one, number 3, is gas collection. So this gas collection is basically from your alternative to practical as well. They can be from metal plus acid reactions. And then you can be from, what's the other one? Thermal decomposition. So group 2, decomposition of the carbonate or the nitrate. So they like to ask you about gas collection. The other one is to do with volumetric analysis. So basically, things which you often see in practical, they can come out as well. So they can ask you to investigate using titration, like percentage of ions. You know, when you have iron tablets, you know, the ladies take iron tablets, right? Because of loss of blood. So they can ask you how many % of the tablet contain iron. then you have to design a practical on titration, for example. Or you could be talking about purity. So you have percentage purity. So let's say you have a mixture. So I'm just talking about scenario here, yeah, okay? So just a little bit of introduction. So mixture of NaCl and also, I don't know, Na2CO3, for example. So this thing doesn't react with acid because it's pH 7 already, but this thing can react with acid. So you can design a titration, find out how much of the mixture reacts with acid, therefore take away how much the mass of Na2CO3 away from the total mass, then you can work out the percentage of impurity, or rather you can work out the percentage purity, how much of the mixture contain that. Are you still with me so far? I mean, these are all things which you would have done in paper 3 anyway, so they are just paper 3 turned into paper 5. Okay so far?
Yep.
In the past few years, a couple of things have gotten very, very popular as well, which is electrochemistry. So this idea on electrochemistry can be divided into two things. There can be electrolysis. This is basically your IGCSE questions. So whatever they come out in IGCSE can come out here in electrolysis bit as well, but they can ask you to do a bit more calculation. Here you go to IT. They can ask you to use the Avogadro constant as well as Faraday constant. So you know F is equal to LE, how many particles you have times the charge of the particle. That's going to give you the total charge for 1 mole of electron, electrochemistry, right? They can give you some marks for the experimental setup of a electrochemical cell. This generates energy, whereas this uses energy. There are two different things. In the cell, they can ask you quite a lot of things, one of which is Nernst equation that has come a couple of times when you have non-ideal condition. Basically, sorry, not non-ideal, when you don't have 1.00 mole per dm cube. Basically, you're not under standard condition. Okay, I mean, there's just on top of my head things that I've seen so far, and there are many more. There's no point of guessing. Do not guess what will come out. Okay, my number one hint for you is do not guess what will come out. Instead, practice on the skills. Do not attempt to do 1,000 papers. That should not be what you're trying to do. You should, when you do one paper, find out what is wrong, find out how you can improve on that before you do the next one. Are you with me so far? Okay, now reading information. Paper 5 is only 30 marks, okay? So you can think about your A2, right? Your A2 has 30 marks from paper 5, and you have 100 marks from paper 4. No matter how bad you are in paper 5, I think you can definitely score 15 because the graph itself, you know, identifying variables, 15 is definitely in the back. You might not get 30, so you might lose 15 there. I don't think you should lose sleep over it. So losing 15 marks is not too bad for paper 5 if you can get very high for paper 4. The trick really is you must really get your marks in paper 4. If you get the marks in paper 5, it's a bonus. And of course, you must get all your marks in AS. That is number one. You must get as high as possible in your AS. There was out of 30 for paper 3, out of 40 turned into 30, out of, I don't know, what have they changed this at all? So 40, 30, 70, that should be, how much is paper 2? Is it 60? Yep, so there's 130 and then 130 there, right? Okay. If you can score as well as you can for AS, that will help you to top up with paper 4. You shouldn't worry too much about paper 5. If you do some work for paper 5, you're not going to fail. But you do not guess the question. You have to practice a couple. Okay, I'll go through a couple of things. Always read question number 1. If you don't understand the objective of the experiment, then how are you going to be able to plan what practical you need to do? So this is the planning bit, the first question. You need to think about whether things are practical or not. So these are common sense, even in physics. You might be like, oh, I think we should have this really expensive apparatus, but do you have it in school? If it is not something you have in your school, then it is unlikely to be possible or to be practical in the school, okay? These are all from the examiner. I did not write any of these. These are just collection of examiner report, yeah? What else? When you specify something, like I have done with paper 4 tutorials, number 1, do not write marking scheme. Okay, do not write marking scheme. Be straightforward. but explain yourself. Do not give like one-word answer. You are not writing a marking scheme. You want to specify. You want to specify stuff, especially when the questions say what chemicals, what apparatus, what are the quantities that you should be using. This is in the planning, yeah? I don't think you have problem with significant figures and decimal place, so I just leave it there. Do not run up too early. This happens with any calculations, really. What else? You need to fully answer the questions. So as you know about planning, planning is usually descriptive. So they need you to describe blah, 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 blah. Use step like step 1, step 2, step 3, blah, 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 so that you can follow your stepwise process. But instead of, doing it from the very get-go, you should try to have like a brainstorm idea on the site. Then when you write, you can look at your brainstorm idea and you know what to write for point number 1, point number 2, point number 3. That way you're working much better rather than, oh, I will, only write as I go along. Then you run out of point. Then you're like repeating yourself, or even worse, contradict yourself. Okay. When drawing graph, I'm sure you know, make sure you use a cross. Make sure you use a dark pencil and you use a cross. A dot is not very good. So this is poor. This is better. This is good. So use a cross to mark your dot, to mark your point. Okay. What else? Obviously, do not, when a question asks for one thing, do not give more than one thing, because they will just mark the first one. If a question asks for 2 things and you give 4 things, they'll just mark the first 2. Even though your last 2 is correct, but your first 2 is wrong, you get 0, because you already provided more than you should, and you're already making a mistake in the first 2. So you don't get any marks for the extra thing that you write. It's just the protocol. If you read a marking scheme, you will see they say any 2, but then sometimes examiner report, they will say they only mark the first 2. They only mark whatever they set out to ask you. They never mark the extra one. Just so you know, yeah. What else? I guess all of this you should really read on your own. I don't want to go through all of these. Reading question carefully, not too important there. Now, how your answer is structured. Please read through this in your own time. Yeah, I've already uploaded in the Google Drive. When you have wearing glove, wear glove. Now, minimizing risk is very important. This is called safety precautions. In chemistry, I don't know about physics because I never did the planning bit in physics, but in chemistry, they always talk about safety precautions. Just because you say you use goggle, that is not going to be accepted, because the examiners, they always consider every single experiment you do in the lab, you're supposed to wear goggle anyway. So that's why they don't accept this, because this is the minimum standard that you must have when working in the lab. Wearing glove is not as good as wear chemical resistant glove. Chemical resistant glove is quite important, because your glove can be any kind of glove. Sometimes you see people handling food, they use the transparent kind of glove. Those gloves are not good for acid. If you're working with acid and base, those gloves will not save you. They will still corrode your skin, okay? What you want is chemical resistant glove. You have seen those colored gloves, the rubbery type. They're called the nitrile glove. Nitrile because they have contained this thing. These are nitrile. And of course, acid and base can hydrolyze nitrile. As you know, base hydrolysis, acid hydrolysis of nitriles can break this triple bond, but it will not happen immediately. That's why it takes time for hydrolysis to happen. That's why it can protect your skin against hydrolysis. Well, I mean, it will hydrolyze. It will take time. That's why it can protect your skin against being corroded by the acid or the base. Chemical resistant glove is good enough. You don't need to say nitrile glove at all, etc., etc., etc. Make sure that when you're collecting gas, you take care of pressure. Pressure and gases do not go very well, yeah? So gas and pressure are very dangerous. You don't want to build up of pressure at all in the lab. Vagueness. Do you understand this term, vague? Vague means not very clear. So you don't want to write like essay, but at the same point, you should be thinking before you write. Okay, so a lot of the times when I mark students' work, I'm sure your work is better than some of my students, but in the past when I mark students' work, they just write the first thing that comes to your mind. Before you write something, yes, the first thing that comes to your mind, you think about it again. Does it make sense? Does it answer the question? Is it enough? Okay, so sometimes they always say insufficient, How do you know enough is enough? Well, if you can look at your own answer and you can critique it, I think this is enough for the 1 mark. I think this is a different point of interest. That kind of skill will really help you in many other subjects. Well, I guess in physics, probably not in math, but I guess you probably know what I mean, okay? It's easier said than done. It's better done with practice, yeah? Okay, this is a very popular question. Do you know what is making up a solution? So this is making up a solution. Have you made up a solution before in the lab, before school were closed?
I don't think so.
You never did the practical? So this is solid. If I ask you, then you put it in the beaker and then you add water. So this is distilled water. So distilled water, you add solid. Then you stir it. You stir it, and then you transfer into volumetric flask. This is volumetric flask. Have you used a volumetric flask before?
Yeah.
So you have make a stock solution then, because you only use volumetric flask if you want to make up a solution.
Oh, I thought you
Okay.
meant like a solution, like a answer to a problem.
Okay. So do you know how to describe going from this step all the way to here? When I fill out my stock solution, when I fill out my volumetric flask, you just add more water, right? You add more distilled water. You have done this kind of thing before. You add it up until the mark, and then you stopper it, and then you shake it. Have you done that?
Yeah.
So you shake in order to mix well. This is a very, very popular thing in paper 3, and it's usually 3 marks. 3 marks, okay? I say again, 3 marks, 2 to 3 marks really. Describe how to make up a solution in paper 5. Really, really common. So they expect you to be able to say, how do you weigh out the mass of the solid? Can you tell me?
Remember the mass of the what's it called?
What apparatus do you need to use in order to measure the mass of the solid?
We need a scale.
You need a what?
Scale.
Can you spell that for me?
SCALE.
This is probably what you use in English, but we don't call it like a scale. It doesn't quite work in chemistry. I think in physics, you probably call it a balance, electronic balance.
Yeah.
Okay, so a scale is more suitable for your body. You know, if I want to measure how heavy I am, I put myself on the electronic scale. But in the lab, I think in physics also, you don't really call it a scale. You call it a balance or just electronic balance. And basically, all of this solid has to go into the solution. Do you agree? So the mole of the solid is equal to the mole of the solution. Do you agree? If all the solid dissolve in the water, but we don't pour the solid into the volumetric flask, we never do that. We always do it in the beaker first, and then we transfer it into here. And then you gotta wash. You gotta wash the beaker, because whatever solid you try to dissolve might not fully dissolve. After you transfer all of it into here, you still haven't reached the mark. You wash the beaker with a little bit of distilled water 2 or 3 times, and then you combine the washing into here. And then still not enough, you add more distilled water until you reach the mark, but you need to do drop by drop at the end. Can you explain why do you need to do drop by drop when you are very close to the final mark there?
Oh, because to get accurate.
Sorry?
How do you say it?
Well, I mean, you did it in the lab, right? You have done it, right?
Yeah.
So when you added more water, you squeeze the distilled water bottle, and then you squeeze it, and then this one goes up. But then you don't squeeze all the way, right? You squeeze until it's very close. Then you take a dropper, and then you open the distilled water bottle, and then you add drop by drop. My question is, do you know why you added drop by drop? Why not?
Because
why not squeeze?
if you squeeze it, and if it goes over the mark, then the concentration is ruined.
So it's about accuracy. You do it drop-wise, not from the very beginning, near the end, near the end mark, because you want to be accurate. That is the purpose, for accuracy, right? You cannot overshoot the mark. Once you overshoot the mark, you cannot take it out because you already have more water in there. So it's gonna ruin, it's gonna change the concentration already, like you said. At the moment, we want all the solid to go into the solution. So your solid is mass over mR, your solution is concentration times volume. And then usually they ask you how to work out the mass. Well, how do you work out the mass? The mass is just concentration times volume times mR. You know what concentration you want. You know what volume you want because the size of the volumetric flask is the volume. The concentration is what you want. The mR of that solid is what you know. Therefore, you can work out what mass you need. Very common calculation to begin with. Do you have any problem with this part of the theory?
Why do we have to put in the solid into the beaker before putting it into the volumetric flask?
Okay, that's because it's never good because if this is solid, if you pour it into the volumetric flask, if the volumetric flask is a bit wet, can you imagine you got a little bit of solid stuck on the side? Is that good? It's much easier.
Can we not wash that off with the distilled water?
I beg your pardon?
Can't we just wash the sides off with the distilled water?
You could, but then that's not the way to go. All right, that's because you are trying to avoid, because this is such a small opening. You see, it's designed in such a way that it's kind of like corn at the bottom, but it's kind of narrow on the top. When it's narrow on the top, you risk, when you have very fine solids, some of them are very powdery. If you pour powdery solid into such a small hole, sometimes the air pressure inside might push out some of the solid. If you lose even a little bit of your solid, is your concentration going to be accurate? If a little bit of the solid fly away? No, right? Whereas this is bigger, this size is big. That's why we always pour the solid. Actually, we never pour it into distilled water. We add distilled water afterward. We add the solid into an empty beaker, then we add the distilled water. Yeah? I mean, that was what you did in the lab, right? Am I correct? Please tell me you did not add it onto the volumetric flask straight away. Did you?
Okay.
You didn't, yeah? Okay.
I think I did.
Oh no. Okay, try to avoid that, okay? Because it's much easier. Can you imagine like you have to stir? Another thing, if you have a solid that don't dissolve easily, if it is a big chunk of the solid, once you put the big chunk in here, what is your plan then if it doesn't dissolve easily? Well, are you gonna pour it out again? You could, but then it might not be accurate concentration anymore. Whereas when you're in a beaker like this, you can stir and stir and stir and stir quite vigorously because you don't add until it's full, right? You just add a little bit of water so that you can dissolve as much as you can. But then you pour it via a con or something, via like a filter, not a filter funnel, via a small plastic funnel, and then you won't lose anything. And then you just keep on washing until you get all the solid as dissolved as possible. That is called making up a stock solution. Are you happy so far?
Yes.
Now, another one which is very popular is dilution. Have you heard of dilution before?
Yeah.
Dilution is another thing which kind of similar to this. I can make a concentrated solution. Then from my concentrated solution, I decrease its concentration. So this is my concentrated stuff. I add water. I just add distilled water. So concentration is very important because you're going to use this a lot in rate of reaction experiments. And that is why rate of reactions is a very popular topic in paper 5 because they can ask you quite a lot of things involving making a solution, changing concentration like this, just add distilled water. If you're just adding distilled water, your mole will not change. Your mole is the same. Yeah, because you're just adding water. So C1V1 equal to C2V2. Agree? Okay, so that should not be that tricky. But of course, based on this, you need to find what is the volume that you need for one of them. So you find out what volume you need. Now the question is, once I get what volume I need, what kind of apparatus do I need to transfer this particular volume of this particular solution into the volumetric flask? Suggest what kind of apparatus should I use to transfer the concentrated stuff into the volumetric flask? So the goal here is to transfer concentrated stuff into here, but I need a certain volume, right? Before I add distilled water to make it up to a very accurate concentration. I want very accurate concentration. So how much of the concentrated stuff I need is based on this formula. Okay, so far? My question is,
measuring cylinder?
Okay, now measuring cylinder. Can you think of a more accurate apparatus in the lab to measure volume of solution?
Right.
Sorry?
You're right.
So which one is more accurate?
You're right.
Suggest why I shouldn't use measuring cylinder.
Oh,
I can, right? Measuring cylinder can measure volume, right? But why I shouldn't use measuring cylinder? Any idea? I mean, you kind of answer your question already just now. If burette is more accurate, why shouldn't you use measuring cylinder? Because
it's less accurate.
because it's not very accurate at all. Okay, does that make sense? You're trying to make something up in a volumetric flask. Volumetric flask, or basically called volumetric analysis, very, very accurate stuff. Very accurate stuff. You don't go and use something which is not accurate at all to make up something accurate. If you use something which is not accurate, no matter how good your apparatus is, it's not going to be super accurate because you already make a mistake of using something less accurate along the way. This happened in physics as well, right? You measure a mass, but then you use like the cheap scale, the scale that is used to measure body mass. Is that going to be good in the lab to measure, I don't know, 0.01 gram? That's not going to be good at all because it probably read it as 0 gram. You can't read it. So you know your precision, your accuracy is not reflected in the apparatus you use, and therefore you lose the accuracy along the way. Okay, so hopefully that makes sense there. That is just dilution. Make sure you know how to do the calculation. Make sure you know about the apparatus. And after you transfer using burette, the calculated volume, then you have to talk about adding distilled water. I need to emphasize on distilled water. Yeah, quite a lot of students, they just talk about water, but you know you need to mention distilled water in your answer. Did you know that?
What's the difference though?
Pardon?
What's the difference?
What's the difference? Okay, if you use water, it is not clear. Is it tap? Is it distilled? And we never ever use tap water in the lab, right? Remember when your answer is vague? Now, water is quite vague, but tap water is not what you use. Never, because this content dissolve ions. Imagine you are doing qualitative analysis, and then suddenly your solution is not supposed to contain other impurities, but then tap water contain dissolved ions, right? I mean, many countries that put some fluoride into the water to help battle tooth decay and stuff, to help people who don't have enough nutrients from food or whatever. Okay, so we never use tap water. Distilled water is pure water, 100% H2O. Sometimes they call it deionized. Have you heard of deionized? Deionized means you remove all the ions. When you remove all the ions from tap water, then you're going to get distilled water. That's basically where distilled water comes from. You get it from the tap water, or you get it from river water, and you remove all the ions so that whatever they boil out at 100 degrees Celsius is just your 100% water. We got to specify this whenever we make stock solution here. And also when we do dilution, we got to use distilled water to make it up to the mark. And you got to do drop by drop, or you do it dropwise near the end to be as accurate as possible. Do not forget, stopper the flask. You got to shake in order to mix well. If you don't do this last step, then how can your solution have a uniform concentration? This is to get uniform concentration. Your job is to get a solution, right? And in order you get a solution from the solid, you still need to do the exact same thing as to get the solution from the concentrated solution. These two, very, very popular stuff. All right, so far? Okay, so not too tricky, right? I told you this is experimental chemistry, things you've done previously, yeah? Now, completing a table and drawing a table, these are getting less and less popular, but if you do older past year paper, they can appear as well. But just because they are getting less popular does not mean the examiner cannot ask. Remember, just because it hasn't come up for the last couple of years does not mean the examiner cannot ask you, because they are still technically part of experimental design. It's part of analysis. This happened in physics as well. You got to know how to manipulate data. Yeah. So basically, you got to label your column, especially when you have to come up with your own table. Back in the days, I think from 2015, previously, before 2015, they usually have around 4 marks for the table, question 2. These days, they usually only have 2 marks because they label everything in the column already. So you're just doing, pressing your calculator. But anyway, just so you know, be very careful what you calculate. Okay. How good are you with your calculator? Have you ever made any mistake, or are you generally okay with pressing your calculator?
I do it multiple times.
You did multiple times. Okay. When you did the paper, when you did the question 2 just now, how long did it take you to finish the table?
Like 10 minutes.
Huh? 10 minutes? For that table?
Yeah.
Including the
Like
graph?
table and graph and everything.
Table and graph. Only table and graph, yeah? Not the questions, yeah?
Oh, some questions too.
Okay, 10 minutes.
One or
Okay,
two.
okay. All right, that's better. Okay. Anyway, so talking about graph. Now, graph definitely, almost definitely in paper 5, you will have graph in the second question. Sometimes you get a straight line graph, much easier. Sometimes you get a curve. Okay, so you need to be aware that sometimes it could be a curve. You cannot draw clearly strong line. So you know in mathematics, precision is required. What else? Do not label your axis incorrectly. You know when you label the y, something, 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 you gotta have the stroke and then the unit. You know that, right?
Mm-hmm.
Okay, do not forget your unit. Yeah, a lot of students they forget the unit there. All right. So this is the x-axis and this is the y-axis. Do you know which one is dependent variable and which one is independent variable? Have you learned about that before?
Isn't the independent variable? Oh, that's the
Have you?
x-axis.
I don't know. Have you learned about this before?
I remember it from IG.
Okay. So which one is the dependent? Which one is independent?
Oh, dependent is what you keep, and independent is what you're measuring.
Okay. So which one is independent? Which one is dependent?
Y is independent.
Okay. Now that's where you're wrong. This is what you change. Okay, sorry, I wanted to hear what you think first, okay? You change the x and then you measure the y. Do you agree?
Yeah.
Okay, as you change the x, then you measure the y. So y-axis is dependent variable. Okay, there's an easy way to remember this. Okay, I got it from my friend, and my friend taught me many years ago, and that is what I've used throughout my paper 5 tutorial. It's quite a funny statement. Why are you so dependent? Do you think you remember that now? Why are you so dependent? I know it's a silly thing, but you know, it works, yeah, okay? Why are you so dependent? Y-axis is your dependent variable. It's what you measure. And then if this is why are you so dependent, I mean, you do understand where this comes from, right? Why are you so dependent? Well, it's kind of like me being angry, but I'm not, okay? So this has to be the independent variable. Okay, so far? I mean, sometimes you get 1 mark for identifying what is independent and what is dependent variable. So you gotta be able to actually, you know, score this kind of thing. No matter how silly things are, there are some stuff that are very tricky to remember or you always forget. Therefore, you have to come up with a creative way of remembering things, okay? Rather than, you know, memorizing blindly. It's not gonna help you. You know, you gotta think of a way for you to remember stuff. That's my point. What else? Blah, blah, blah. I think the rest should be okay.